Now I'm going. Today we're going through more thermo. So we're going to go through the same stuff that we did yesterday or Wednesday, a little bit less, a little bit slower, and then we're going to get to actual results. So I'm going to do, where did the good copy of the notes go? I swear there was a good copy. They were right on top. I guess that's the best copy I got. Yep, okay, that is a good copy. All right, so thermodynamics. So remember the first thing I wrote down yesterday? The first thing I wrote down yesterday is called the first law of thermodynamics. So the first law says du equals dq minus dw. But almost always, we write this as du equals dq minus p dv. P dv is the work done by the gas. So have any of you ever used canned air to like spray off a keyboard or something?
Yeah.
These aerosol air cans. Or really any other aerosol can. A can of spray paint will do the same thing. If you spray something, if you're a tagger or whatever, if you spray a can of an aerosol fluid, it gets colder, right? Why does it get colder?
Change in pressure.
Pressure decreases.
Pressure decreases and
Volume's constant.
volume's constant, and
Thermodynamics.
so the volume, the density goes down. So the specific volume goes up, right? So you do work, PdV, against the system. So that gas is expanding. It's expanding into the rest of the air. It's doing work. The gas is doing work against the air that it's expanding into. That drops its temperature. Why? Because du is CV dt. And the gas is really at a constant volume. So this is a little hand wave. You don't take too much out of that. So du goes down because you've done work. So the internal energy goes down because you've done work against the system. And then the temperature goes down because the internal energy goes down. Right? Okay, so that's where we start. And really, a lot of what we're doing stems around chain rule. So we're going to have a lot of equations that look like, well, we're not going to, but when you get to thermo, you're going to do this a lot. But I'm going to do it a little bit so that A, you've seen it, and B, I kind of need it. So we write down our total derivatives. So remember, there's 3 state variables that matter. There are more than that state variables, but only 3 are independent at any one time. So I can write down my total differential as du dA at constant b dA, and this is a partial, and this is a partial, and this is a full, plus partial u partial b at constant a dB. And then through a bunch of trickery that we've got that you'll see when you get to thermodynamics, there are relationships between all of the various state variables that you get by pulling this stunt a couple of times. So, the first thing that we talked about was CV. Actually, I'm going to start writing equations over here that I like. Oh no, I'm going to use the other board because the other board makes sense. Sorry, I'm a little squirrely. So we'll write du equals dq minus, let's call it PdV, because that's always going to be, because everything that we do is going to be with an ideal gas in this class. And what else? We said that du also equals CV dt, or also equals nr dt, or equals k over mu mp dt. Okay? So, so that's the specific heat at constant volume. You can see that the specific heat at constant volume, CV, is just nR. We also need the specific heat at constant pressure. So where are we going today? Let's talk about what I actually want to accomplish today. So the thing that I want to accomplish today is the criterion for convective stability. So what that means is I've got a pot on a stove or whatever. I've got something that I'm heating from below, and I've got some temperature gradient from the top to the bottom. So what I want to know is how big does that temperature gradient have to be for it to start to boil, for it to start to actually convect. So I'm going to set up T1 is much bigger than T2. So how low does T2 have to get for it to start to convect? So if you've ever made pasta, how many of you have made pasta before? How many of you? What was that?
Butter noodles is the best.
That's right. That's right. I mean, pasta is a staple of food, right? So if you ever watch the pot get hot, it just starts to sit there, and you have the fire on, and it slowly gets hotter and hotter and hotter, and then it starts to boil. Yeah.
How does thermodynamics explain that a wash pot never boils?
You're just
I
impatient.
got something. There's something hilarious there. I'm sorry. That's a good slow pitch. I should be able to hit it. I'm just gonna whiff this one. I'm sorry.
It's okay.
That's a good setup. I'm sorry, man. There's such a good setup for a joke. There's got to be a quantum mechanics joke in there too, right? Because quantum mechanics is all about observing things.
You can think about it. I'll ask it again next question when more people are here.
That would be dope. Yeah. Make me look good. Okay, so so if you've ever watched your pot boil,
Can't change state while you watch it.
Was that?
Can't change state while you watch it. It has to be unobserved to be in the state.
That's right. That's right. That's right. So eventually, bits down here will start to rise. So when does something float? Why does this start to rise? Because the density is low, right? So when the density of this little blob is less than the density of water, then it will start to rise. So what we're actually going to do is I'm going to say I have some star, and it has a temperature, and we're going to call this temperature of the star, and a pressure of the star, and a density of the star, and these are both decreasing functions of radius. Okay, so the density goes down. Why does the density go down? Well, yeah.
And also heat, pressure, like radiation.
Let's do something really dumb real quick.
Density goes down as radius gets bigger, is that what you said?
No, I didn't say anything actually.
Oh, okay.
I hadn't said anything concrete.
I'm making
I just
stuff up.
said why does density go down? So let's talk about why density goes down real quick. Let's do it. dPdr equals minus rho g. Do you believe me on that, or should I derive it?
You should derive it for fun.
Yeah, but it's quicker if I don't. So dPdr is force due to pressure, right? And mg is force due to gravity, right? Now we're using force per unit of volume, so it's rho g, and it's minus because it's pointing down, right? Does that make sense? They're pointing in opposite directions. So let's just real quick say that T is constant. Only reason I'm saying that is because it's easier to solve the differential equation.
P pressure.
P is pressure. Thank you for clarifying that.
It's not momentum.
Yeah, that's a capital P if you can't tell. So we're going to assume the temperature is constant. So P equals rho T times K over M, right? So rho equals, actually let's do it this way. So we'll just plug this in. So we'll say that d rho dr, and then I have a tk over m, and we're saying that's constant. That's why it comes out of the derivative. So I'm just plugging in p into here, equals minus rho times g. We'll rearrange this a little bit. We get d rho dr equals minus g over gm over kt. This is an energy over an energy. This is the mass of the hydrogen atom times rho. Okay, this is a differential equation that I want everybody to make sure that they have good and memorized. So the only thing that depends on r here is rho, so what's the solution to this differential equation?
E to the negative gmh to the kt times r.
Right. So rho equals rho naught, that's whatever your boundary condition is, e to the minus gm over kt times r. Or we can rewrite this. Actually, let's rewrite this a little bit. I'm going to call this r over h. And I'm going to rewrite this as, I'm going to upside down this. This is now kt over mg minus 1. We're going to call this 1 over h, right? So now I have this thing that looks like a height. So now when my density goes, so now when my radius goes up by this height, then my density has gone down by a factor of 2. Does that make sense? So how can you think about this? Gravity's pulling in, so the pressure and density gradients have to be pushing out. So they all have to go outwards. So the density has to go down as you go outwards. Because gravity's pushing, because pulling in. So pressure has to go out. So this also is a good way to define the pressure scale height. The pressure scale height H is P over G. And you just do the same thing but with pressure instead. And you get the same equation except now you have a pressure scale height. So the pressure scale height is where it falls off by
And
a factor of E.
g is also dependent on r, right? Or is
Um,
it the g on?
yeah. So let's just pretend we're at a tiny little spot where G doesn't change very much. So just think about a little tiny space. And then you'll have to do it again, to do this again in spherical coordinates with whole stars. Yeah.
What is the exponent in d rho over dr? The bottom one.
Oh, that's a minus 1.
Minus 1. And
Yeah.
is that 1 over h part?
Yeah, so this is 1 over h, where I'm just defining h this way.
Okay. Oh, I see. Okay.
So h is equal to, 1 over h is equal to
Oh, yeah.
mg over kt.
Okay.
Okay, so back to this. So density, pressure, and temperature all decrease going outwards. So now the 3 state variables I'm dealing with are going to be density, pressure, and temperature. But I'm also going to have to talk about entropy. But that's not a state variable that I'm dealing with. It's just going to help me out. So what I'm going to do is I'm going to start with a little bubble, and I'm going to have rho of the bubble, T of the bubble, and pressure of the bubble. And I'm going to take this bubble, it's going to start off here, where everything's in equilibrium, and the pressures and densities and temperatures are all the same. Then I'm going to pull it up here to some new distance, to some new point, and we're going to look at whether or not its density has gone down. And if its density goes down to below what the star is doing, then it'll keep going. But if the density doesn't go down far enough, then it will fall back down. That make sense? So we have 2 possible modes. One is an oscillating mode, and if you're a physicist, this is the Brunt-Vasaya process, and if you're an oceanographer, it's the Vasaya-Brunt process. For whatever reason, they're always backwards.
Darn oceanographers.
I know. Or if the density is high enough, then the blob will keep going and keep rising. So what we're going to assume is that this blob rises adiabatically. So how many of you are comfortable with the concept of adiabatic? How many of you do not know what the word adiabatic really means and want to talk about it?
I'm so confused.
That's all right. So we'll talk about what adiabatic means. We're going to talk about entropy first. So let's see. When I'm winging it and I don't have slides, sometimes I skip stuff. Do I need to do CP again? I'm not going to do CP again. I'm just going to jump straight to entropy.
What does that mean again?
Was that entropy?
CP.
Oh, okay. CP is. Let me write those up here.
Sorry,
No
I
worries.
know we talked about it last class.
Heat with a constant pressure.
That's it, okay. I just have a bad memory, I guess.
No worries. Specific heat at constant volume, and CP is the specific heat at P equals constant.
Man, that
Now we
wave
don't
is-
really need, so the only thing that I need is that CV plus NR equals CP. And there's this quantity gamma, which is CV over CP, CP over CV, that is gonna show up in a second. And then this is the only thing that we need to worry about, is gamma. So the specific heats are related, they have some relationship, they're slightly different quantities, but they're related this way. But gamma is the thing that we need. Gamma tells me how squishy the gas is. It tells me how many degrees of freedom I have. No, I need that thing. So I'm not gonna derive this CV plus NR equals CP. I might make you do that for homework. Because it's a really valuable thing to do, and also good to do more than once.
Did you do that yesterday?
I did.
Monday?
Yeah, I did it Wednesday, so I'm not gonna do it again.
Wednesday?
I'm gonna move on to the new stuff. So entropy. What is entropy? What do you know about entropy?
Chaos.
Chaos.
Media doesn't understand it.
I confuse it with
Nobody
enthalpy.
does.
Everything.
What's that?
becomes-
I confuse it way too often with enthalpy.
Oh yeah, it is not.
Enthalpy.
Amount of disorder in a flow system.
Uh-huh.
I know nothing.
Energy?
Yeah.
Everything-
What's the something else?
Energy?
It's not an energy.
I mean,
But like you can get energy.
Energy loss?
Yeah.
It shows that
Doesn't
thing
it, like-
when things aren't like time reversible.
Time reversible.
Doesn't it like interact with surroundings
Oh.
too?
Closed systems.
Closed systems do what? A closed system. What does entropy do in a closed system?
Stays.
In,
Or
in
Doesn't.
Or doesn't
increases.
the only thing it doesn't do is go down.
That's what I'm saying.
Yeah. So in a closed system, goes up at best, or does nothing. The important thing that nobody has said yet is it's also related to heat flow.
Did you hear me say that?
Was that?
Oh.
I'm sure we all said that in unison
I
like
know.
5
I think
seconds
there's
ago.
more
So-
to us all.
I think every single one of us said that.
I know. I heard it.
Try to find it.
We all
Okay.
said it.
So ds is defined as dq over t. Full stop, right there. That is what entropy is heat flow over temperature. Now, I talked a little bit yesterday about heat flow not being a state variable. Heat is not a thing that you can get back out. You can't return to a particular state of having heat. Heat is a thing that moves. But entropy is a state variable. So this combination makes it a state variable, which is weird. So entropy is something like temperature or pressure, that if I do something, but as long as I get back to the same state, the temperature will be the same. So I've got 3 state variables that are independent. And then I have, so say I've got temperature, pressure, and volume. If I have some gas at some temperature, density, and volume, and then I do a bunch of stuff with it, but I get it back to the same temperature, pressure, and volume, The other state variables all go back to their original quantities as well. Entropy is one of these. So if I do something to a bunch of gas and then I put it back to where it was, the entropy will go back to where it was, even though it's about heat flow. So in the late 1800s, they knew that entropy was this thing, but this is what they knew about it. They didn't know about this part. They didn't know about the chaos or the disorder. It wasn't until statistical mechanics came along and really showed what entropy is at a fundamental level, and showed that it has all these other properties, that made all these things make sense together. Make sense for some value of makes sense. So from a just thermodynamics point of view, entropy is just a measure of how much heat can flow out of a system. So heat flow, also it's a, okay, so now we're going to talk about what adiabatic means. Adiabatic means ds equals 0. Now we're okay, this is d, this is a tiny little change in s. You never write down s as an actual quantity, even though it's a state variable. It's a weird thing. The only thing you care about ever is the change in entropy. Because the absolute value of entropy doesn't matter a whole lot. Only the changes in entropy matter. So in an adiabatic process, the change in entropy is 0. So what does that mean? That means the chaos and the disorder stays the same. That means that it's time reversible. It also means there's no heat flow. So it means all of these things, right?
What was before the heat flow?
Time reversible?
Oh.
I don't understand anything.
Which part don't you understand?
Just general confusion.
Well, let's back up to where I lost you. So entropy is this. It's just heat flow over temperature. And that's not something that you're going to be able to get some kind of deep, rich understanding of why this is. It's just the definition. Yeah.
So in an adiabatic,
Uh-huh.
whatever we start with, something occurs and we can still get back to where we started.
In any process. Well, yeah, in any reversible process, yes. In an adiabatic process, that
that's
also
going
is
on
true.
here.
That is also going on here. But more importantly, no heat is flowing through the system. So ds equals 0 also means dq over t, but t is never infinity. So dq is also 0.
So it's either just, it's reversible or it's just not flowing.
That's right.
Okay.
Yeah. Yeah.
So this is just like an ideal situation.
Adiabatic?
Yeah,
Well, no, it happens pretty much all the time.
really.
Yeah, whenever you have a process, because it's about heat flow, but really adiabatic is about heat flow and time scale.
So,
Okay, so I can heat something adiabatically by doing it very quickly, or I can heat something isothermally, or I can't heat something isothermally. That's dumb. Isothermal means same temperature. So I can't heat something isothermally, that doesn't make any sense. But I can compress something isothermally. So say I've got a tube with a piston on it. If I slowly squeeze the air in the tube, it can stay the same temperature as the surrounding gas, and that's an isothermal process. So it'll stay the same temperature. But if I do it really quick, if I do it faster than the heat conduction time scale out of the bottle, then the heat can't flow and it gets a lot hotter.
Oh.
Does that make sense?
So that's how PTV works.
As what?
That's how PTV works on like a time scale.
What's PTV?
Like PTV, you know the PTV law?
Oh, yeah.
Or PV over T? PT over V?
perv nerd.
The ideal gas law of this one?
Yeah.
No.
PV over
The
T equals
the
PV over
combined-
P1 V1 over
combined-
T1 equals P1 V.
the
Oh,
combined
P2
gas
V2
law.
over.
Combined gas.
Yeah, that's that. That's just that twice, right?
So
I just put a
Yeah.
1 on these and then a 2 on these and I divide them and I get all of those variables.
Yeah, because NR is
Yeah,
constant.
Yeah, and ours
Yeah.
constant.
Yeah.
yeah, because one's
So yes, it's like that.
Okay.
So it's related, but those three things don't tell me how quick I'm doing it.
Yes.
So they don't tell me about the heat flow. So PV equals nRT doesn't tell me about the heat flow It only tells me about those three, how those three things are related. So when I do it quick, then the heat is all trapped. And I have another law that I'll show, well, I'll write it down. P equals K, which is some constant, rho to the gamma. I'll show you this one. I'm going to derive that in a second, but I'm going to write it down over here. In an adiabatic process, P equals rho to the gamma. There's a constant in front, so it's a proportional, but so let's derive that now. So we're going to do this process where we pick our little blob of stuff up kind of quick so that the heat doesn't flow, and then see how dense it is, right? So that's the stunt that we're going to play. First, we got to show that P equals rho to the gamma.
What is K there? Just some
K is a constant.
Just any, like it's not a specific one that we know already?
That's right. So that's a constant that comes out of the boundary. So this is a boundary condition constant.
Which I assume you've given to us.
Yeah, you'll be able to sort it out. So from this, the thing that you can really say is P1 over P2 equals rho to the gamma, rho 1 over gamma over rho 2 to the gamma. So you can say that, and then the constant goes away. Almost always that constant goes away. Now I gotta do this, sorry. I gotta do the derivation in my head before I do it in front of people so that it's all there. So give me a second. Okay, now sorted. Okay. So I'm gonna take a bottle. Oh, I'm gonna write this over here. That's the important thing. In an adiabatic,
Also, at least once, you should totally tilt the camera so we can see all the things you've written at the end.
oh yeah, that's a good point. Thank you. Yeah.
Just
thank
like
you.
at the end, like
Yeah.
all the important takeaways. Sorry, Connor.
Yeah,
Yeah.
that's a good idea.
That's for
a
you,
good
Connor.
idea. Yeah, thanks, Connor. Where am I? Okay, so
Pour one out.
pour out some code for dp. Okay, PV equals nRT. So dp dr. Okay. nRT. I'm going to write it a little different way. P equals rho t k over mu, and okay, this is the same thing. Mu mp is just the mass of the particle. Mu is the average mass of the particles, and that can change. So if I've got like something sticking together, so if I like have a cloud of atomic hydrogen and I'm forming molecular hydrogen, mu is changing in that process. So mu can change sometimes. So for 1 second, I'm going to let it. So dpdr is just, we'll just use chain rule. We'll use chain rule, and then we're going to divide through by p again. So I've got 3 terms here. Rho, t, and mu. So I'm going to have 3 terms in my derivative. So dpdr is p over rho d rho dr minus p over mu d mu dr. That minus sign comes from the fact that mu is on the bottom.
What's that second term again?
d
Sorry.
mu dr.
Before that one. No. Other way.
So dpdr is p over rho d rho dr minus p over mu d mu dr plus p over t dt dr. I'm not going to derive that. It's just a chain rule, but I might make it a homework question just so that you see where this comes from. and I've done a little bit of refiguring because, you know, if I just do chain rule, then I'm gonna have dp dr equals tk over mu d rho dr. But I can just rewrite this as pressure divided by density. Does that make sense? So okay, now let's keep our materials fixed, so the concentration is fixed. So we're just going to write dpdr as sorry. This is why I was reading the derivation. Start again. Let's take a mulligan. I'm going to step back a minute, erase the thing that you just wrote. I started that one wrong. I started doing the next thing down.
The whole 3 terms.
Yeah, that whole chain rule thing. I'm going to do that next.
Hey, it looked good though.
Was that?
It looked good.
Yeah, it looked good. It was great.
I believed you.
Fair enough.
du equals minus p
I don't know what you're talking about.
dv. Why can I say this? Well, so du is q minus p dv, but this is an adiabatic process. So now I've got an adiabatic process, so dq is 0. Okay, so du is just p dv. So I can take PV equals nRT, and I can take a derivative of this, and I'm left with PdV plus VdP equals TR dN plus NR dt. Does that make sense?
Yes. Chain.
Chain rule. Chain rule, but I'm differentiating with respect to nothing. So we're going to fix the number of atoms, so we'll get rid of that one. And, oh, dt, I know that du, du equals minus p dv, du also equals cv dt, so that I can say that dt equals minus p over cv dv. This is just a little bit of algebra, but I want to make sure that everybody believes me. So dt is minus p over cv dv. I just get it from du, dv. And this guy, I'm going to plug this into here, and I'm left with p dv plus v dp equals nr over cv p dv, and that's a minus. I picked up a minus sign there. So I'm going to multiply through by cv, and then I'm going to get cv times p dv plus cv times v dp equals minus nr p dv. So now I've got a dv here and a dv here. I'm going to take this over to the other side, and I've got cv plus nr dv. This is just cp plus cv v dp equals 1. No, 0. I'm going to divide through again. So this is just cp. So now I have cp dv plus cv v, p dv plus cv v dp equals 0. Oh, I missed it. I dropped a minus sign somewhere. This has got to be a minus sign. And then I divide through by cp. And remember that gamma is cp over cv. And I'm going to divide through by, I lost a p, a pressure and a volume. So I'm going to be left with 1 over gamma dv over v equals dp over p.
And so where did that minus come from?
Let's see, I dropped it somewhere.
It's on the floor.
Oh, no, I'm sorry. That's plus.
There's a plus.
That's a plus. because I'm supposed to have a minus sign here.
Okay, cool. So it's CV plus NR PdV plus CV dP equals 0.
And this turns into gamma because I'm dividing through by a P and a V. So I get a dV over V and a dP over P. This one's minus and I get a gamma here.
Okay. I'm connecting some dots, yeah.
Good, good.
Can
Yes.
I'm still conceptually shaky on, is dv and dp and dt, are they derivatives of some functions or are they tiny pieces of v, p, and t?
Sure.
Is it both?
Yep. It's the one of those that you need it to be.
Okay.
Because derivatives and tiny little pieces of things are related to each other, right? A derivative, f prime of x, is just df, tiny little part of f, over dx, a tiny little piece of x. And we just make those tinies tiny, and then I have the derivative. So there's a tiny, so you can think about them as tiny little pieces, or you can think about them as changes. Both are fine. Both are equivalent, and you'll get used to which one is the more useful thing as you do it some more.
Yeah, this has just been the most confusing part about like having derivatives in physics. It's like you have a specific function in math, and then you have just like a dt, like what with respect to what, dt with respect to what.
Yeah, so if you just have it by itself, just think about that. That's a tiny little piece, and I can turn it into a derivative, but by itself, it's just a tiny little piece.
Okay.
So that statement, gamma dV over V equals, that's a negative dP? That, right, that negative.
Is the line above that a negative?
That's just, that is a true statement about adiabatic systems.
Yeah.
Okay.
What is?
So this right here,
Oh, okay.
I have not done any approximations or thrown anything out,
Okay.
which is a thing you always should check, because I throw a lot of things out, and I'm going to throw some stuff out in a second. This is just a true statement that's always true. This is as true as PV equals nRT.
And that's only for an adiabatic system because dq is 0.
Right, exactly. It only works because I could say this. I could say that dt is just a function of dv, and that's because dq went away. So now I've got to solve this. And that's actually super easy, but maybe if you don't know how to solve it yet, then it's not super easy. So what is dv over v? Here, I'm going to start this in the second word, because we're going to solve that bit. Times it.
Just solve like 11 and 12 minutes.
Yeah, I'm not going to
9
get
minutes.
the second bit that I wanted to get to though. Okay, so gamma dv over v equals minus dp over p. This is equal to gamma d log v equals minus d log p. So this goes up here. D log v to the gamma equals d log p.
And one would not write
I'm gonna move the sign from
log
the sign.
dv. It's, you would write d log v.
No, I wrote log dv. Wait, I wrote d
You
log.
wrote d log v. I'm
You
saying
can
that's
also
just,
write. You can also write log dv, but then you rarely would do that.
oh,
How did I get that log?
Yeah,
No.
so,
Both of you first. How did I get that log?
mhm.
I'll do that in a second.
Okay.
oh,
I still can't see how you went from those last couple to that final sort of.
Oh, I got from here to here?
Yeah.
Okay, so that's, let me do that again. So I got CV plus NR times P dV equals minus CVV dP. So this becomes CP. So that becomes CP. And then I divide both sides by CV. And I just get gamma. And then I've got gamma PdV equals minus VdP. So I'm going to divide both sides by PV. So that cancels this, and it leaves me with a 1 over V. and it cancels this and leaves me with the 1 over p. That make sense? No, you
I
know,
was just confused on how you got the gamma, but the rest
the,
was
the gamma came from,
Over
CV.
there.
yeah, these guys and this guy, they all turn into gamma.
Is it just an arbitrary constant of CP over CV?
It's not arbitrary, it's
Or-
5/3, basically always. Sorry, 5/2, or 7/3, 7/3. Oh crap, squirrel brain is totally letting me down. It's 5/3 or 7/3, 7/5. But you don't have to write any of that down, because I haven't talked about what gamma is. It's not arbitrary, it's very specific, and it's a very specific number, and it's actually simple to deal with. But right now, you just need to worry about it. It's a property of the gas. The only thing it depends on is what the gas is made of. So gamma is one thing for a monatomic gas, and it's another thing for a gas that has 2 molecules. But that's it. So then I divide by V and P, and I'm left with this. So now,
Did you integrate both sides to get there?
yeah, I magicked this V inside of here to make it a log. Let's talk about that for a second. dV over V. Okay, what's the integral of 1 over x dx?
It's natural
I
law.
let X.
Log of x.
But why are you still multiplying that by d?
Yeah, that's
like,
what I
why
was
is
wondering.
why is that inside of the?
Because I haven't integrated.
But you
But you
kind of
did.
did.
No, I haven't yet.
Wait, so
I just changed it. So if I take a derivative, so let's talk about this one for a second. Actually, let's back up all the way.
What?
So
So you
integral
integrated
of 1
but
over
didn't
x dx. No, I didn't integrate. Equals log x.
Okay, then how did
Right?
it
Yes.
So
become?
if I'm just going to take a derivative of both sides of this, and the derivative kills this integral, so I'm just left with 1 over x dx. But
Yeah.
the derivative doesn't kill this, so this is still d log x.
so you're taking the derivative of the integral.
Okay.
Yeah, I'm magicking it.
But okay.
There's just, these two things are just related, so
So you're both integrating and differentiating, so you do nothing, but you can write something different.
yeah, actually that's how I would think about it.
Yeah, because I was gonna say you're basically just canceling everything that you just did.
He's doing nothing by doing two things that cancel each other.
But
That's
the
how you
logs
do
make
it.
Right,
it
it's
easier to
different.
work with.
Yeah.
Was that?
But the logs
That
make it
actually
easier to
makes
work with.
I'll show you, yeah. Logs make it easy to work with. So
Because every time it's tricky, log makes
So-
it backwards.
all of thermo is about turning things into full derivatives so that I can integrate a full derivative.
Word. Okay.
If I have d house,
D
Ooh,
house.
what kind of house is it?
House M.
it's a little 2,000 square foot thing in Kalari, so you can charge a lot for it.
Sweet.
If I integrate this, I get house.
Why would you want to integrate it though?
Well, because then I get a whole house. This is a building house.
This is
Oh, that's a partial
But,
house.
That's
but
like all your drywall and shit.
Oh wait, so
if
that's
I have
a
the
mobile
integral
home.
of
What
dog
if I'm D person? A house.
D house, I can't just integrate dog D house because I don't know how to integrate that unless I know the integral of dog or whatever, right? So let's be a little bit less.
What would you say the integral of dog is?
Maybe 2 dogs.
4 legs? Oh, 2
Dogs.
dogs, that's, yeah.
Dog squared.
How many legs do
Okay,
that?
it's okay.
Dog squared over half a dog.
Yeah, so, okay, let's back to where we were. So I got gamma dV over V is minus dP over P. Oh yeah, I was making a dog house. Okay, that could have been so much funnier.
Missed the joke there.
Was there more joke?
No, that was the
That was
dog
the-
house. Yeah.
So alright. So we're here, so we got here. Everybody's comfortable with how I got here.
Yes.
We're not quite sure with what I'm doing next yet.
So.
So-
Log magic.
So I'm gonna do this log
Dog
magic.
house.
So d log v equals minus d log p. And then this gamma is a constant, right? And what is constants, what does stuff out front of logs do?
Exponents.
It goes into the exponents, this becomes a gamma. And I'm gonna take this minus sign and I'm gonna put it up there too. Right? I can put it to the other side and then it's in front of this. And then put it up there. Good?
Math.
Math is math, right? You can just do that.
I have this really bad.
So I get to kick this minus sign way the
I
hell
did
up here.
that.
I love logs. Logs are really the best. They're so entertaining. They're really the best. So now I've got d something, right? So what's the integral of d something?
Something.
That's something.
What's that? Which part do you hate?
Yes.
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 Can we go back to doghouse?
This is the part I'm following more than any of the previous part of the lecture. Like,
No,
this
no,
is just
no, I
math.
got the other stuff. It's just your little log magic.
He integrated it and then differentiated. He wrote an expression that is true of that integral and then differentiated.
Oh, okay,
both
so
So
they're
sides.
get it in terms of a log.
So
Yeah.
you can get it in terms of a log.
So we want this in terms of a log.
Yes.
I want it, so I have a thing, the reason that I do it is I have 1 over v times dv and I don't know how to integrate that.
Okay.
Because I don't know what
Oh,
v
because
is,
you use a log.
right?
Okay, okay.
But if I can get this to look like d something, then I can integrate it and I'm just left with something. So that something is a log.
Okay.
So the reason that I'm doing it is to get a full derivative. The method is this, you integrate and then differentiate again, like
Okay.
real quick once, real quick.
Okay.
Does that make sense?
Yes.
All right. It is a minute, that's why I'm spending time on it, like, we're spending class time on it, it's weird. Now I have a thing that I can integrate, right? So now it's a full derivative here and a full derivative here, so the d's just go away. And I get log of v to the minus gamma equals log of p plus a constant. Then I exponentiate everybody. And I'm left with v to the minus gamma equals, let's call this v naught. That's where this constant's gonna go. Log of p. No, not log anymore. Get rid of it. We're done. Just v equals p to the minus gamma. Or, if I treat this as minus rho, this is p equals rho to the gamma equals p. So the reason I wanted to spend, that was all of class time, was just getting this relationship. But the methods are very important, and the math is pretty entertaining. But the result is very important, so this is a super valuable
Rho
result.
to the gamma equals v naught.
Equals
v.
p. P equals rho to the gamma.
Yes, and it also equals v naught v to the negative gamma.
Yeah, and they were writing this as a k. So it's just the integration constant, whatever that means to
Yeah.
me. So,
Again, they use different letters.
I know. It's
because
like
the
we
thing
have-
is, the letter doesn't matter.
We have KB, we have K,
We have kappa.
Kappa. It's
Yeah.
just,
And
they
then-
love that.
Yeah.
Because it's Germans. They're just like constant.
Yeah, K is for constant. Okay, that's it for today. I will do Schwarzschild on, midterm week after next.
Week after next.
Week after next.
So the 11th.
Uh,
Saturday.
We already took the midterm.
We have another one.
Got you there.
more tests. Let me pull it up. Let me pull it up.
Thank you.
Do you have it on this on the calendar?
I'm just going based on that, so we got.
Oh, let me pull up the calendar that I wrote. Oh no, that's the wrong spot.
Oh, see, I thought we started it this week with the dummy.
No, this week is simple harmonization and it's
I totally told her it was wrong.
Try it, you can try that.
And it's okay.
gonna be on the paper that I write.
I was like, it's next. Last week I was like, it's next week. And
I'm pretty sure I killed an entire forest of trees with the amount of PBS.
Yeah, the 15th.
oh, I know.
Oh man, did I really do that to myself? NSF grants are due on the 15th too.
Oh,
That's all right.
On the 15th?
What's that? The midterm is on the 15th.
And what else did you say about 15th?
National Science
Na-
Foundation.
NSF grants are due then, so I have a bunch of crap I have to do in addition to that. So
So it doesn't apply to you.
there will be a homework due the day before. It's not up yet. It'll be up on Monday.
Will that homework help us with the test?
Yes, it's going to be what's on the test, and then we'll go over it on Monday.
I like
So actually, okay.
Are we ever going to use the ABCD papers again? That you gave us?
What?
Squared,
No.
yeah,
The voters.
It was a great
Voters,
idea.
that's the
I was
word.
so excited.
And then you just
Oh.
lost it.
And then I actually, so the reason that I did that is because I wasn't sure this is a bigger class than what I've wrangled before, so I did that as a mechanism to be able to talk to you guys but you guys actually talk, so I don't need them.
Well, at least a select few of
Go
us.
us.
No, I think most everybody, like, I see all of you, like, most people aren't here on hold on, most people are engaged in the wake, so.
When are we gonna go into reading questions
Maybe I
again?
should get a turban.
Someday I'm gonna do it.
That was
So,
probably
a lot of the reading, so this is a very good question, so he asked when are we gonna go over the reading questions again? A lot of the reading questions lately have just been, can you go over the Saha equation? Which is what I'm gonna do in class. Like last time. So a lot of them are just like, can you go over this bit, which is the stuff that I'm gonna do. There are some questions that I do need to pick up, so I am following behind.
You know, most of mine has been, what the heck is happening?
Oh yeah.
Is it real Muppet?
I don't know what they did or didn't do to get the fabric, but all I know is it's on me right now.
Did it violate the Geneva Convention?
There was a,
I can have a confirm
Was it
with
a
that.
crime against Muppets?
there was a sketch comedy outfit called The State back in the 90s, and they had this one sketch where they were like, this guy's eating this like big fluffy thing, and he's like, what are you eating? He's like, it's Muppet.
Especially
What
in
the fuck
Spanish.
is it Muppet?
Fair?
I'll show you.
Oh, yeah.
I wish I knew the difference between near and far. I'm just pounding the door, and Muppet shows up, and he's like, here. He runs away. He's like, oh, back and I beat the shit out of him.